Hi everyone, thank you so much for coming. It's a real pleasure to be here back at QCon. I haven't spoken here for a while, so it's always a treat. It's my favourite conference. So as Nikki said, my name's Ben. I work at a company called Confluent. So we're one of the companies that sits behind Apache Kafka. I expect most of you know Kafka if you're on the streaming track at QCon. So I used to work on the technology itself. I wrote the latest version of the replication protocol, throttling a few other things. These days I work in the office of the CTO, which is a slightly more general function. And one of the things we did last year was we actually looked very closely at the differences between stream processors and databases. And this led to a new product that we have. It's called ksqlDB. But actually, it's actually pretty interesting, I think, to sort of compare and contrast the different models. And both the way that we interact with data that's moving and interact with data that is passive or resident. And that's sort of what we're going to talk about today. But before we get to that, I wanted to start by taking a little bit of an aside. And I think this helps phrase why it's important in the future that we do get a degree of consolidation. So there's a very good post by a guy called Mark Andreessen. He's actually an investor out in Silicon Valley. And this post basically says that software is going to end up eating the world. So, if you're an investor, you probably want to invest in software because over time we're going to consume more software. Like you guys will be buying more applications on your phone. Companies buy more software that makes their business more efficient. That's like a general trend. But actually, if you think about it, there's a couple of different forms of this. Right? This is sort of like weak form, like basic idea that we as an industry just consume more software. But there's actually this strong form. And the strong form is interesting because it's, in this particular way of thinking about it, our businesses become effectively more automated. So it's less about just us buying more software, companies consuming more software, and more about actually taking our business processes and automating them using software. So that's a bit abstract. So what does that mean? Well, think about something like a loan processing application. Right? So loans, this could be this could be a mortgage that you're taking out or some other kind of collateralized loan. This process hasn't changed for 100 years, pretty much. There's a credit officer, there's a risk officer, there's a loan officer. And each of them has their particular stage in this process, and we have some software that makes it more efficient. The companies have, will write or purchase software, which makes each part of this better. So we're sort of helping the credit officer do their job better, or helping the risk officer do their job better. That's kind of the weak form of this analogy. We'll buy more software to help these people do a better job. These days, you can actually get a loan application through in a few seconds. It's like a traditional mortgage will take maybe a couple of weeks because it follows that manual-driven process. But today, in these more contemporary applications, these more contemporary companies, you can automate the whole thing. So this is still using software, but it's using software in a different way. It's using software which is effectively talking to other pieces of software so that you can automate the process of getting a loan very quickly, in a few seconds. So if we think about that, what this actually means for the architecture of the systems that we build, if you want to help a credit officer do his job better, that's where the three-tier architecture comes in. We have our user, they talk to a user interface. There's some kind of back-end server application that's running behind that and a database, and you're helping the user, let's say, do risk analysis more efficiently or whatever it might be. But as companies become more automated and those business processes become more automated, we end up with services talking to one another. This is like software talking to software. It's less focused on the idea of specifically helping a person and more focused on achieving some end goal, some business end goal from different pieces of software. So a good example of this is like a taxi, like ride-sharing applications. So in these, you actually have streams of events, right? So your phones, both phones in the on the customer side and on the taxi driver side both have GPS information which is being streamed back to these server-side applications. You have many different services running in the back end. They're doing geospatial matching to try and work out which taxis they should send alerts to ask them if they want the ride, buffering the responses to work out whether or not, to work out which is the most efficient driver for a particular user, etc., etc. So you've got streams of events. You've also got like business events. The fact that you actually decided to accept that particular ride. So all of these different software, all these different pieces of software sitting at the back end allow you to automate this process. This is very different to like phoning up a taxi company and asking them whether or not you can have a cab arrive at your house at some time. And this is only possible by basically automating the whole process. Many pieces of software talking to many other pieces of software. And you see the same thing in the evolution of software architecture. So the monolith to the distributed monolith to like microservices. These are all implementations that involve, well, certainly the second two, implementations that involve distributing your processing, but it's mostly focused on users. It's mostly focused on the user interface. Actually, the data that lives in a microservice architecture is actually often joined together on the front end. Right? So the user interface is actually talking to a bunch of different services. The front end is actually kind of doing that join because it's displaying different parts of the page to the user. But what happens when you want more data-centric things? Well, that's where you tend to get into event-driven microservices. This is a pattern where you still have the user interface, you still have servers, application-side server-side programs which are responding to those, but you're journaling events which then allow you to decouple an architecture and do a lot of the mechanics which makes the business work asynchronously. So you've got that kind of user-centric side, and then what we might call this software-centric side. We're actually automating the business and we're growing an architecture. So why am I telling you all this? Well, this trend kind of leads to this idea that the user of the software in the future is likely to be more and more, not just you and me, not just users of an application, but actually software which is talking to other pieces of software. So what does that mean for databases? Well, just think for a moment. Maybe close your eyes. Actually, you don't need to close your eyes. But you can maybe figuratively close your eyes and think about what a database is. You've all used databases. Many of you, I'm sure, use them every day. And certainly you will have all used them at some point. So what does it feel like to use a database? You write a query. And there's some server off in the distance somewhere, and it's got lots of data on it. And you can write this query which allows you to answer a question. And there's like no way you'd ever be able to answer that question yourself because there's like too much data and your mind can't pass through it. So you can send this question off and you can get an answer. It's wonderful. Right? It's a really powerful idea. That's what I think of when I think of a database. I've spent many years building on and working with databases. And we actually have hundreds of these things today. They all kind of feel the same. Right, so we have lots of different variants. Something like Cassandra will let you store a very large amount of data for the amount of memory that it's using. Something like Elasticsearch provides you with a very nice, rich, interactive query model. Neo4j will let you do something like query the relationship between entities, not just the entities themselves. Things like Oracle and Postgres are kind of workhorse databases that can kind of morph to different types of use case. So there's hundreds of these different things, and they all have slight different variants that make them more appropriate to a certain type of use case. But they all have a couple of fundamental assumptions, and one of the main ones is that the data is passive. The data is just sat there on the database waiting for you to do something. So the database, as a piece of software, is actually designed to help you. It's actually cast as a technology because it grew up in a time when we built applications that were designed to help users, whether it's you or me or a credit officer or a risk officer or whatever it might be. So if there's not a user interface waiting, if there's not somebody sitting there clicking buttons and expecting things to happen, you've got to ask the question, well, does it have to be synchronous? Well, one alternative is to use event streams. It's just like a different way of doing it. And stream processors are a technology which allow us to manipulate event streams in a very similar way to the way that databases manipulate data that's held in files. But they're built, importantly, for active data, and they're built for asynchronicity. So let's just classify what that means. If you think about a stream processor, it actually has a very different model of interaction. Anybody here use something like ksql? A few of you. Okay, keep your hand up if it felt like using a database. Oh, we got one. So I actually think it feels quite different. You can sort of make it feel like the ksqlDB, this like newer one, does feel like one. But ksql feels not so much like one, and it's because of this interaction model. This very familiar interaction model that we get with the database, we don't really quite get that with a stream processor, because a stream processor isn't really designed for us. So a traditional database, the query is active and the data is passive. So what does that mean? That means that this is about what initiates the action, what makes things happen. In a database, you make things happen by running a query. The data is just sitting there passively waiting for you to run that query. If you're off making a cup of tea, the database doesn't do anything. It's just doing nothing. You have to actually initiate that action. In a stream processor, in event stream processing, it's the other way around. The query is passive. The query sits there. It doesn't change because it runs forever. It just sits there on the server running. And the thing that makes it do something isn't somebody running a query, it's data. It's some event happening in the world, something being emitted by some other system, or whatever it might be. So this is a very, very different interaction model. So with that in mind, I want to dig a little bit more deeply into some of the sort of fundamental structures that we have in stream processors and compare how those relate specifically to databases. And probably the most fundamental one is this concept of streams and tables. Because I think streams kind of define in many ways what a stream processor does or an event streaming system does. So stream processors work on events. This sounds like a very simple idea. In fact, it is a pretty simple idea. We can record what happens in the world based on a number of events. This could be somebody placing an order, maybe they're buying a pair of trousers. This could be you paying for the pair of trousers. It could be you changing your customer details. It could actually be the position of your phone, sort of another kind of continuous event streams. It could actually be a whole bunch of different things. It's a record of a fact, something that happened. But actually events as a data model are slightly different because they include this notion of intent. They tell you about a state change, not just the state. So to take the kind of canonical LinkedIn example, if Bob works at Google, that's the state. That's the state of Bob at some point in time. The event would be that Bob has moved from Google to Amazon. And the reason that that's subtly different is that typically when we drive processing, we drive our applications, we don't just want the state, we also want to be triggered off these state changes, off this intent. So stream processors are always forwarding these events, this intent, this fact that something happened so that you can react to them. So a stream is an exact recording of exactly what happened, published, normally in a topic. And a table represents the current state. And this is actually important because we're going to come back to it. This idea of recording absolutely every single thing that happened, recorded in a stream. And if any of you have used like event sourcing, it's a very, very similar concept. This idea that we're keeping this journal of every single state change. If we want to derive our current state, we can do that by replaying the stream. So the stream tells us like where we've been versus where we are now, or payments that you've made versus your account balance. Or a way that I really like to think about it is to use chess. It's like a good analogy. It's like I can think of a table, like a database table, as being the position of each piece, right? So I can take the position of each of those pieces, and that tells me my current state. I could store that somewhere and recreate it if I want to. A stream works the other way around. It takes a sequence of events from the starting position at the start of chess, and then we can replay all of the moves, the events, the state changes, to get us into the same position. So streams don't just tell us about the position of the board at a point in time, they also tell us about the game. They tell us about how we got there. So what's this got to do with databases? Well, we can actually think of a stream as a type of table. Actually, no real reason to call it a stream. Well, we'll get to that a bit later, but a stream can definitely be thought of as a type of table. Right, it's a particular type of table that doesn't exist in most databases. It's immutable. You can't change it. And it's append only. So in a table, I can have insert, update, and delete. That's mutable. It has a notion of a primary key, which is also important. So a stream can be considered as an immutable append-only table. If I write a value, it's automatically going to be recorded forever. Can't go back and change that. And the reason I can't change it is because it might have been consumed by somebody else. If I want to change it, I have to make another record, write another message, which is actually then going to propagate that change. That's why immutability is so important in logs. It allows us to recreate the state through a sequence of facts. So stream processors communicate through streams. Input streams go to output streams. But internally, a stream processor, even though that model is stream to stream, internally, they're using tables. This is actually a bit like the way in a database. A database, when it runs a query, actually uses temporary tables to hold intermediary results as it's doing its computation. You can't see them, they're temporary. In a stream processor, they're not temporary because a streaming query runs forever. It doesn't run differently for each user. Or for each request. It's just like one query that's running concurrently. But it does contain this notion of tables. So in this case, I have like payments coming in on the left-hand side as a payment stream. Then I'm running some credit scoring function. So that's going to basically collapse the stream of payments, which we can think of as a sort of a table of payments, and aggregate it by user, so that each user has a credit score. So my table is actually smaller than my input stream. And the stream processor then listens to that table and provides the output as another stream. So when we use the stream processor, we create tables, we just don't really show them to anybody, because what we're trying to do is read streams of data and output streams of data. So this leads to this duality, this kind of stream table duality, where the stream represents history. Every single state change that's happened, I can apply a projection. It could be something as simple as a group by key, which is basically involves just creating a table that has the latest version for each key, which is what most people would think of as a table when they use a database. And then likewise, you can listen to a table, listen to all of the things that change inside it, and create another stream. That stream won't be the same as the one that you started with if your table is using an aggregation, because you sort of lost data. But you can maintain both of these. So you have this kind of duality. Streams can go to tables, tables can go back to streams. This is actually very similar to the notion of a materialized view. So a materialized view is a construct which is available in many databases, notably relational ones. And it came from this idea of an active database, which was popular in the 1990s. But there's a couple of big differences. So in a stream processor, we have a stream, our input is a stream. We have our aggregating function or logic or whatever it might be, which is going to create my table. And then that outputs as a stream to another application, so another application can react to that. So that's asynchronous, and the query is basically a push query. It's running all the time, and it's creating new results. In an active database, the input is a table. Right, so we have a table. Remember, these two things can be similar. We can create an append-only table in a database. And then we have a function that runs, creates our credit score. And then if we want to interact with that, well, we have to send a query and get a result, right? Because it's a database. So in this case, there's two big differences. The whole process inside of creating a materialized view is synchronous. It's like locked inside the database, often inside a transaction. And the interaction model is a pull query. But this represents a very similar concept. It's just that the way that we interact with it and the way that data moves around is different. There's a big similarity between materialized views and stream processes. Okay, so let's look at joins. Joins are another way that these things are sort of similar and sort of different. So a stream processor can do joins. Databases mostly can do joins, or many of them can do joins. So are these things exactly the same, or are they slightly different? On the most part, they're quite similar, but let's look at how a join works in a stream processor. So let's there are a few different types of join, but we're going to start with a join to a table. And this is a very simple idea. We have a stream of orders coming in here, and a stream of customers, which is going to be materialized inside this table. And we're going to enrich each order with some customer information. And that's our stream processor. And basically, the orders come in, we do a lookup in the table based on its primary key. Right, so with this table, there's actually an event stream behind it, and it's got it's effectively doing a group by key to materialize the table. And then what we get out is an order joined to its customer information. That's pretty simple, right? It's actually almost exactly what a database does. So a database reads data from a file. It would read the orders from the orders table. It would have an index, maybe on customer information, or maybe a primary key on that table, and it would just look up the values inside a query. So very, very similar, the way these two things work. Big difference a database has is a database knows about the data that it's got. Right? It can maintain like statistics and stuff that tell you about the cardinality of that data. And that helps it decide whether or not to use indexes and stuff like this. In a stream processor, you don't know what's going to arrive next because it's like real-time data. So you can't really make those optimizations. What about joining two streams? That's a bit different. So the thing about a stream is you know less about it. That table, we can kind of index it, we can look it up we can give it a primary key. With a stream, that's not quite the case. So the way this works is, in this case, we've got Bob's order. Bob and Jill have orders, and we have payments, and we're joining orders to payments. So maybe like, Bob bought some trousers, and then he made a payment, and we want to kind of collate them together. And because the system's asynchronous, these things could be reordered. And they could both be reordered and turn up late. So actually, Bob's order is behind Bob's payment with respect to Jill. So as these events move into the stream processor, what happens is Bob's payment comes in and it gets buffered inside a little index. Jill's order goes into the buffer also. Then Jill's payment comes in. And we can do a match. So each time these are processed, it's looking for the corresponding side, a corresponding event on the other side. It's also actually checking the event time. It's using event time to process that, but we'll come back to that in a bit. And then Jill's order and Jill's payment come out as a joined unit. So only when both of these things were available do we actually get an output. It doesn't matter which one came first or came last, more importantly. Only that's the point that we'll actually get the output. And then likewise, Bob's order comes in, is matched, and is sent out. So the reason this is a little bit different to a database is that this is actually using like a well, there's a couple of things actually. One is that you're only buffering so much data, which means you can handle these very high throughput use cases where you don't want to maintain the whole data set inside a table and index it and look it up on the fly. The other one is that often these streams, remember the streams are a history. They're like a history table. They hold all of the different versions of a particular event. So if Bob bought a pair of trousers and then he decided to change his order, you'd actually have like a set of different orders for versions of an order for the same thing. So in this case, maybe like a change from boots to boots 2. So we've actually got multiple different values, multiple different state changes from the same entity inside this stream. So if we just treat it as a table, well, we get like this Cartesian product. That'd be like pretty inefficient. You get like loads of data coming out all the time. So stream processors handle this by allowing you to correlate things in time. This is where windows come from. So we can use like a time window to basically restrict how we're going to join a data set. So if we want to correlate these two things in time, but also by their identifier, we can use windows to do that. It's very hard to do that inside a database. So we have this idea of including in a stream processor the ability to correlate recent events in time. Something you can't really do in a database. And you can actually do more advanced versions of these. So a session window is another interesting thing, also quite hard to do in a database. So a session is like you decide, you're like looking for trousers on your website, and then maybe you buy some, and then you go away. So you want to just detect some period of activity that then ends. So a session window will allow you to do that. It has like a no defined length. It just goes on for some period of time, and then when there's a period of inactivity, it's dynamically ended. The other thing is late and out of order data, because things obviously change. One of the things we talk about in stream processing is the idea it's hard to work out where the end of something is. Like when does something end? When does a day end? When does a computation end? So in a stream processor, you can actually use window functions to create outputs which you send out, and then you're actually using time to correlate when something comes in, which window it should go into. So you have this notion of history, you can update previous windows, and this lets you handle late and out of order data. So stream processors provide a bunch of tools that let us handle asynchronicity. They allow us to leverage time. It's like time in any distributed system is kind of hard to work out or hard to reason about, but time in this concept, in a stream processor, you can have system time, effectively, or stream time, or you can have event time, which is a time that the event was actually created by the client. And you can configure the system to use either one. And then, so they let you leverage time, and then they also let you focus on the now. Stream processors are designed for this processing, which is about real-time events. So they're kind of similar. There's similarities there between the way that joins work, but there are also some differences. What about data placement? So stream processors use a two-tier storage model, most of them. The different ones use actually slightly different approaches, but they're all quite similar. So storage is normally in a streaming system, something like Kafka. Flink actually uses something like Kafka as well as maybe HDFS for snapshotting. But effectively, we can think of it as just being some distributed storage layer. And then streams are processed as they arrive, because the storage layer is not just like a file system, although Kafka actually architecturally looks a lot like a distributed file system. What's actually happening is obviously it's pushing data towards you, or at least conceptually it's pushing data towards you. So you can react to streams in real time, but if you want to create tables, you need to materialize those. And this is actually done inside the stream processor. So a table, if you have a table of customers, that will actually be materialized inside the stream processor itself. This is actually very similar to the way that databases work. So if you look at something like Snowflake, Snowflake has a back end, it's an analytics engine, and it materializes tables locally so that it can do efficient elastic processing. Data is also partitioned. It's actually partitioned in two different levels. So you're partitioning on the storage level, Kafka stores data in a bunch of different partitions on a bunch of different machines. So if I have some data set of orders, it's actually going to be spread across all of these machines. Likewise, in the processing layer, we're also going to spread the data across multiple different machines in different partitions or shards. And that allows us to process things in parallel. Big problem with doing this, though, or one of the problems, is that if you want to join things, they have to be partitioned in the same way. So if you want to join orders to payments, you have to make sure they both share a key, so that the order and the payment that corresponds, or the payment that corresponds to the same order, ends up on the right machine. You do this by applying a key, and if you don't have the right key, or your previous bit of processing didn't use the right key, you have to do a shuffle and redistribute data, which is relatively costly. But this is the same way, it's the same process that distributed databases use. Another thing distributed databases use is broadcast, the ability to broadcast data sets to all nodes. And that's actually to avoid this problem of shuffling. So in a partition data model, you have to kind of reshuffle if you want to join from a key that wasn't the key that was used in the previous operation. So you can broadcast a join using, there are different ways of doing this, but in Kafka Streams in KSQL, there's a thing called a global table. And this creates a copy of the data set. So let's say I want to join orders to customers. Orders is a big fax data set. Customers is relatively small. By comparison, also typically would change not that frequently. We can actually broadcast that to all of the nodes. So I can have partition data of my orders and replicated data. It's the same copy on every single processing node, so that I don't have to do this shuffling. I can do more joins efficiently. So architecturally, there are actually many parallels with data warehousing. This idea of facts, well, events and facts are quite similar. Right? They're often pretty much the same thing, a record of every single thing that happened. And dimensions are these things that you want to look up. Customer information, account information, those kind of things. They're relatively small. And actually a lot of the technology that backs this, the patterns of being able to process a query and distribute data to different nodes in different ways, are actually the same across both. Really similar across both. So finally, we kind of get to the idea of the interaction model. So we talked about this before a little bit. A stream processor continuously processes input to output using event streams. Right, that's the way that you interact with it. It's very different to the way that you interact with the database. The query runs continuously and outputs results as soon as they happen. And we saw this slide before, the traditional database, the query is active, the data is passive. In event streaming, the data is active, and the query is passive. So our databases have this notion of a pull query. This is what we call a pull query. What's Ben's credit score now? Well, I ask a question, and I get the result back. In a stream processor, the process is running all the time, and every single time that table changes internally, we're publishing out a result. So we can create a hybrid of these two. Why do we need to just have one? And this is kind of where we think things are going. So in a hybrid stream processor, a couple of things are different. Certainly, firstly, the interaction model doesn't just handle queries, requests for responses. It also handles event streams. So I can have a payment stream coming in. I can be, again, computing my table. Right? So I can summarize and materialize those credit scores. But because that's a table, there's actually nothing to stop me querying it. I can send a select statement to that, get a response. But at the same time, I can also listen to changes on that table as they happen. I have kind of like both interaction models. So what I think we're going to end up with is a kind of unified model. And it really manages two big differences. There's a bit more to it than this. We talked about the different types of joins and stuff like that. But fundamentally, the two big differences are handling both the asynchronous as well as the synchronous, and having an interaction model that is both active and passive. So what does that actually look like? Actually, it's pretty simple. Remember, we can actually think of a stream as being like a table with a different interaction model. And then we can run queries using SQL. So a standard database query basically just runs from the earliest bit of data. And it runs right the way through to now. And then it stops when it gives you the answer. That's the query model that we're all used to. Standard stream processing query. Well, that starts at now. Right? It doesn't consider previous data, not unless I ask it to. It can do. It can go back in time and reprocess everything. But we can store all our data in Kafka for as long as we want. But it doesn't have to. So typically it will start at now and just kind of run forever. Just keeps running forever. There's another interaction model, which is like this dashboard query. So in this, we're starting from the earliest record. And we're querying through to now, but then actually going to keep going forever. So this is, I call it a dashboard query model because it's a bit like loading data into a dashboard and then keeping it up to date. Although this is actually slightly nuanced, because when you do that initial query, what do you actually return? Do you return like just a snapshot from now, which is like the latest version for each key in the table, or do you return all of the events, or some combination henceforth? Because the future data, that's going to come one event at a time, or at least when your windowing function is, if you're using suppression. So we have these different interaction models, but there's some sort of subtleties about how we actually might want to phrase that data. We might want that snapshot. We might want to have every single state change that happened in the past. But we put it all together and you kind of get this unified model where you have like the earliest to now, earliest to forever, and now forever to represent different types of queries. And we can represent these in SQL. So a push query would look like regular SQL, select user, credit score, orders, etc., where row equals Bob. But we have to have this amid changes, which says we're basically going to execute the query and then keep giving you extra results. Or you can just do a standard pull query. So in a standard pull query, we're literally just going to ask a question, and we're going to get an answer. So that's like the interaction model. That's one part. And the other part is this idea of embracing synchronicity. That's another thing that we think needs to change, or we think increasingly is going to change. So in an asynchronous world, that's actually, if you think back to the sort of microservices slide, the idea that we're going to connect these different things together, different parts of a system together. We often want to do that asynchronously if we're automating a business process. Different microservices want to have different life cycles, they want to be decoupled, et cetera, et cetera. So we actually want to be able to orchestrate across different processes. We might want to pull data out of a database, push it into event streams, perform some processing, push it into an application, maybe into a Lambda function or something. So this idea of pipelines is actually something that ideally we want to be able to embrace, along with this interaction model, and having the sort of joins, aggregations, time handling that's required to manage this kind of asynchronous world. Another thing is transactions. Transactions in a database are actually very different, well, fairly different from transactions in a stream processor. So in a transaction in a database, it's actually, you do effectively a two-phase commit protocol when you're actually changing or reading data. In an asynchronous system, what you actually do is you pass barriers. So barriers flow through the various different operations inside the system. And those barriers are actually committed. There is also a two-phase commit protocol, but it's based on these barriers that flow through this system. This is how you can basically manage transactions, manage updates to various different places in a sort of atomic way, using an asynchronous processing system without having to do this sort of two-phase commit that we used to have back in the days of J2EE and that kind of thing. So we have asynchronous pipelines. There's a couple of other important variants I wanted to mention. Stream processors today, most of them are actually frameworks. Right? So although like Flink has a SQL API, Kafka Streams has ksql, there are a few others that do SQL-based processing. We definitely think that's the right way to talk about data. You typically want to talk about data using a declarative language. That's one thing that the relational database world definitely got right. But many of them are actually programming frameworks based on JVM. Most of these are based on the JVM. And that actually gives you a lot of power. You can write anything that you want. You can interact with these tables directly. You can build a different type of application. The other side of this is active databases have also improved. So we have things like MongoDB, Couchbase, RethinkDB. These let you listen to change streams on tables, which is, again, quite similar. Right? But don't have the sort of temporal functions or the handling of asynchronicity and creating materialized views that you get inside a stream processor. So it's definitely like a path of consolidation going on here. And I think we're going to see a lot more of it. So at the start, we talked about this idea that software is eating the world. And that the user of software today, as we kind of automate our business processes, is less likely over time to be a user. It's less likely to just be you and me. It's more likely actually to be some other piece of software which we're sewing together in some automated architecture. And to do this, we think you need both the asynchronous and the synchronous. You kind of need to be able to handle both of these things. You also need these different interaction models. You need to be able to query passive data sets and get answers for users that are clicking buttons and expecting things to happen. But you also want this proactive interaction model where data is being pushed as an event stream to different subscribing services. So we still need all of these. We still all need all of these different types of database. But we're likely to see this shift happening where we start to get different niches of forming around these active databases. And ksqlDB being one example of this. But you're actually seeing other movements in the database community going in the same direction, particularly around active databases. So my final thought for you is, if any of you did close your eyes, which I'd be surprised, but when you saw this slide before, but even if you did it just figuratively, and you thought about what a database means to you, you thought about how you interact with a database, maybe as things change, so does that notion, so does that thing that we hold so dearly, that idea of what a database is. Maybe it needs to be something slightly different to what it is today. And that's me. My name is Ben Stopford. I work at Confluent. You can catch me on Twitter. You can send me an email. And if anyone has any questions, I'd love to have them. Thanks very much.
Do we have any questions? I can see. No. I might have one, actually. So when do you see this sort of standardization happening and the emergence of this new kind of database? Do you see that something happening quite soon, or what is your kind of time frame on that?
So I think there's actually a lot of activity in this space. You're seeing a lot of different database vendors embracing streams. I think maybe we sort of see this more closely than others because we kind of watch it. So I said like Mongo has event streams, Couchbase has these things. I think there was a talk earlier about interacting, or databases that can interact with the front end. That's another burgeoning field. Like a lot of front end development is event-based, and yet most databases don't really handle the event-based side of things. So we're definitely seeing some change in that area. From a personal perspective at Confluent, I mean, we have ksqlDB. We're investing heavily in that, and we think that's actually the way that stream processing is going to go, because it gives you this kind of unified model. And actually having the familiarity of a database with a lot of the processing capabilities of a stream processor is a really powerful combination. So we definitely think it's going in that direction.
Cool. Are there any other questions out there? Can't really see. I think that's probably all then. All right, well, please give... Was there? Oh, sorry, didn't see that hand.
How about moving into more of a data lake architecture directly rather than just a database?
How about moving to a data lake architecture? Well, I think a data lake is in some ways another type of database. Everything you say here you can think of from a sort of operational database perspective or from a sort of analytical perspective. But I think probably the big difference with stream processing, these two things are not the same. A stream processor and actually event stream processing is mostly about sharing data between different places. That could be different microservices. It could be collecting data and pushing it into a data lake. So I think that certainly the way that we've been going with this is to provide tooling that lets you kind of automate those processes. So you can suck data out of one place, materialize it somewhere else, and you can do that using a single SQL layer, effectively. But at the same time, the actual query model, I think it's unlikely that we would use that. We're not going to be a replacement for like a big analytics database. It comes back to the sweet spots. So there's no way that I think you'd see this kind of technology necessarily replacing big analytic systems in the short term. But certainly around like communicating different information around a company or information around a microservice architecture. And most importantly, probably just creating materialized views. So a lot of the sort of serving layers that you want to create, you can do that with this kind of technology very, very well. I don't know if I answered your question. You're welcome.
Any more? All right.
Cool.
I think that's all. Thank you so much, Ben.
Thanks very much.
Let's give Ben a big hand. Thank you.